Hello everybody, welcome back to the BHS channel, Biochemistry for Health Sciences channel. Today we shall talk about the chemicals in our body, and again focusing on aspects that are useful for the healthcare professional. So just to remind you, the organization of this channel is based on the book Molecules to Disease, and we are now going to be talking about, in the next few videos, these two chapters, 2 and 3. So the first chemical we're going to talk about is water. There are several chemistry concepts related to water and the respective medical applications. Let's look at a few examples. So one of the most important chemistry concept for the healthcare professional is the solubility of a chemical in water. This is very important because there are several medical applications of this, including the variety of stones that can form in human beings, kidney stones, gallstones, and so on, and the life story of chemicals in your body. What does the chemical do in your body? How is the chemical absorbed into your body? A, how is the chemical transported throughout your body? D, which is distribution. How is the chemical metabolized in the body? Depends on the solubility of the chemical in water. Eventually, how is the chemical excreted out of the body? Depends on the solubility of the water, or of the chemical in the water. Okay, so very important chemistry concept. Concentration, another very important chemistry concept related to water, and there are several examples of this. Clinically, most of your clinical lab tests, not all of them, but most of them, which are quantitative in nature, they measure quantitative concentration of a chemical in the water part of your blood. Then we have other very important concepts. Osmosis is a chemistry concept which helps us explain how water travels between the various compartments in your body, and we'll talk about these compartments in a few seconds. And then we have concepts related to osmosis, such as osmotic pressure, osmolarity, RET, osmolality, L, osmolar gap, tonicity, and so on. And all these chemistry concepts have very important medical applications, such as intravenous fluid therapy, the phenomenon of osmotic diuresis, edema, as well as hemorrhage or blood loss. Before we get into the properties of water that are medically relevant, let's quickly look at the basic chemical structure of water. As we all know, water is two hydrogens connected to an oxygen atom through a covalent bond. Now, oxygen is a more electronegative atom compared to hydrogen. Electronegative. What this basically means is that, remember a line, this line here represents a pair of electrons. Electrons, as you know, are negatively charged, so this pair of electrons prefer to spend more time. The probability of finding these electrons around oxygen is higher than finding these electrons around hydrogen. So that's what we mean that oxygen is more electronegative. It tends to attract electrons more towards itself when it is paired with a partner, such as hydrogen in this case. So because of this, the oxygen gets because electrons are negatively charged, the oxygen gets a delta negative, and delta here simply means a partial negative charge. It's not a complete negative charge, but there's a very slight negative charge on the oxygen end of water. The hydrogen end is, because the electrons are spending more time here, we'll get a delta positive, a slight positive charge. So there'll be a slight positive charge at the hydrogen end. So we can represent water with a slight negative charge on one end, slight positive charge on the other end, and we call that a dipole. It's like having two poles, a slight positive pole and a slight negative pole. Okay, and we will just represent water like this. So water is the most abundant chemical in our body. About 50 to 60% of body weight is basically water. So there's water everywhere. Water surrounding cells, water inside cells, water outside cells, as well as water in the blood vessels. Okay, so a lot of water everywhere. So in the average 70 kilogram human, there is approximately 42 liters of water. Again, these numbers that we are giving in these videos are very approximate, depending on the size of the person, sex, and so on. Since fat adipose tissue is devoid of water, the percentage of water in an average female or in an obese person would be slightly less than in an average male or a thinner individual. So water, because of the dipole nature of water, water has a lot of very beneficial properties to sustain life, and that healthcare professionals have to be aware of. So at body temperature, that's 37 degrees Celsius, water is a liquid. It's a liquid. It's not a solid or gas. It's a liquid. And therefore, it can act very well as the solvent of life. So as a solvent, many chemicals can be dissolved in this solvent. That's why we call it a solvent, the solvent of life. And once chemicals can be dissolved, a lot of biochemical reactions can happen in the presence of water, and these biochemical reactions create things or destroy the physical constituents of the body so that cells are able to maintain their structure, grow, as well as divide. So as you remember from your basic chemistry, chemical reactions can take place at appreciable rates only in liquids and gases, which allow free movement. Okay, liquids and gases, the molecules in liquids and gases tend to move quite a bit. And in a chemical reaction, the reacting chemical, let's say A reacting with B, they have to move. They have to collide with one another. Okay, and if the energy is appropriate and the orientation of these chemicals is appropriate, then we may form a bond between A and B. Okay, and that's called synthesis. So in metabolism, that's what happens in anabolism or synthesis. And the reverse, breaking this, is breakdown or catabolism. So all these reactions, they require movement. And since water is a liquid, there is a lot of movement, which is very, very important. And because of the liquid nature of water, another very important activity that happens in the human body is transport. And transport is basically movement. Okay, there's transport, this is very essential, transport of chemicals within cells, transport of chemicals between different parts of the body. So transport is very important for survival of the human being, and water being a liquid whose molecules move quite a bit allows for this transport to happen very well. The dipole nature of water also allows water to provide a very important property, and that is to maintain the structure of cells as well as the three-dimensional structures of organs. Okay, so it's important. It's an important role in maintaining shapes of cells, shapes of organs, and at the molecular level, the nature of water allows large molecules, and we'll look at that later, so sort of a chain. These large molecules include DNA, what we call macromolecule chains or protein chains, allows these chains to fold into a certain shape, and by the process of folding, so the nature of water allows this folding into a certain shape, and this shape is then responsible for carrying out the function of the protein. Again, we'll see later, proteins do a lot of things for the cell. So the function of the protein depends on the shape. The shape requires the chain to fold, and all that is possible because of water. Water is also responsible for the formation of membranes. Because water is everywhere, membranes are able to form because of water, and we'll talk about this later under lipids and the formation of membranes. If that's not enough, well, water has even another function. Water can dissociate to give you acid, H+, or base, OH-. So water has a buffering capacity. So it can help us withstand strong acids or bases and protect us against the dangerous effects of acids and bases. Water also has a very large specific heat capacity due to its dipole nature, due to its chemical structure. It has a very, very high, one of the highest specific heat capacities of any liquid. And what that basically means for the healthcare professional is that it's not easy to cool or to heat up water, which means water is very useful for temperature regulation. Okay, so that is very important because humans need to maintain their temperature close to 37 Celsius. Okay, so it helps us regulate temperature because of the nature of water. If a lot of heat is produced here, the heat quickly can travel to different parts of body and keep the whole body at close to 37 Celsius. Okay, that's due to the high specific heat capacity of water. So you can see water has so many properties that help us survive. So the 42 liters of water that an average human has is distributed in various compartments. So inside the cell or intracellular, there's about 28 liters. Outside the cell or extracellular, or what sometimes we call as tissue fluid, or interstitial fluid, there's roughly about 10 liters. And inside our bloodstream, intravascular compartment, there's roughly about 4 liters. Okay, 4 liters of water. Total blood volume is about 5 liters, but then about 1 liter or so is occupied by red blood cells and white blood cells, as well as all the solutes, proteins, and lipoproteins inside the bloodstream. Being a very small molecule with only partial charges, so basically it's uncharged, neutral, water can easily get out. So here would be the endothelial cells that line the blood vessels, the capillaries, for example. Water can easily get out of the capillaries of the blood vessels and then get into the interstitial fluid. And then water can even go through the cell membrane, because it's so small and the cell membrane is a dynamic nature. Or water can go through proteins present on the cell membrane, what we call aquaporins. So water is distributed or travels very easily in and out of different compartments. Very quickly travels to different compartments. Since the bloodstream connects all body compartments, connects the whole body, the amount of water inside blood, or the plasma volume, plasma is the part of blood without the cells. The plasma volume plays a very important role in many physiological processes. So plasma volume can change as water gets out of the bloodstream or water gets into the bloodstream. And this movement of water between the different compartments depends on a process called osmosis, and we'll talk about this a bit later. So too much water in the blood is not good. We don't want hypervolemia. The amount of water must be VOLUML. Let's do this again. Hypervolume, VOLEMIA. So too much water is hypervolemia. We don't want that. Too little water in the bloodstream is hypovolemia. And that too is not good. So we need to regulate the amount of water. Water regulation is very important for optimum health. Water in the bloodstream also is responsible, or partly responsible, for blood pressure. Okay, so part of the reason why we have blood pressure is due to the presence of water. And blood pressure, as you know, is very important to make sure that all organs, the lungs, the heart, the digestive system, and so on, get optimal perfusion. Optimal perfusion. They get enough bloodstream because the bloodstream provides many important chemicals to these organs, as example fuel and oxygen, and which is so critical for energy. Without energy, nothing happens. So water is an important contributor to the blood pressure, which ensures that all organs have sufficient supply of nutrients as well as oxygen for survival. So besides the bloodstream, water is also an important component of other biological fluids. For example, the synovial fluid in joints has water. Urine, of course, is mostly water. Cerebral spinal fluid, the fluid around the brain and spinal cord, has water. Saliva has water. The lymphatic fluid has water. Okay, all the digestive juices as well as stools has water. Tears, sweat, okay, and so on. Vomit. These are all fluids that contain water. So in health and disease, the amount of water in the body can be affected by the release of these fluids. For example, these fluids such as vomiting or excessive sweating can lead to dehydration, and excessive vomiting can lead to significant losses of water, which can then cause various signs and symptoms. So as previously mentioned, the amount of water in the body must be kept within a certain optimal amount. Water enters the body mainly through food and drink, and water is also produced during metabolism, especially during energy metabolism. We'll see basically the hydrogens from the fuel will be reacting with the oxygen that you take into your lungs, and one of the side products, one of the products of this would be water. And then we, of course, have to make sure we don't have too much water. So we have to get rid of this excess water. Okay, and one of the best ways to get rid of water is through the kidneys. Okay, through the urine. But there are other ways of losing water: exhalation, sweating. You can see as much as 3 liters can be lost a day depending on the weather, and then evaporation from the skin. So these are all rough estimates. These values may change drastically for individuals under different physiological conditions. For example, an individual with a fever may lose more water than a healthy person due to the higher temperature that increases water evaporation from the skin surface. Okay, so the first concept related to water is solubility of a chemical. So because of the nature of water, water can dissolve certain things. Dissolve. So what do we mean by when a chemical dissolves? So for example, if I took solid sodium chloride and added that to water, added a small amount to the water, you will see eventually the solid disappears. So what happens is the water molecules come and surround the sodium ions as well as the chloride ions. So it's basically breaking the attachment between the sodium and the chloride ions, and instead of seeing solid sodium chloride, what you see is sodium that is dissolved. In chemistry, we represent this as aqueous sodium and aqueous chloride. Okay, so that's how these ionic compounds dissolve. Now, I should mention here calcium phosphate. Water, it has a very hard time dissolving calcium phosphate, as well as calcium oxalate. Okay, so some calcium salts are very hard to dissolve, and that's why they tend to form things like stones. And as you know, calcium phosphate is an important part of bone. Okay, bone is a solid in a human being. So some chemicals, some calcium salts are very difficult to dissolve. Organic chemicals, those organic chemicals that have certain groups, such as the hydroxyl group, the amine group. Okay, so nitrogen and oxygens are very common in nature. Nitrogen is more electronegative than hydrogen. Oxygen, as you know, is more electronegative than hydrogen. So these kinds of organic chemicals also tend to have some sort of partial charges, and that's why water likes them. Water will come and surround or get attracted to these groups such as hydroxyls or amines, or carboxyls, which have a negative charge, or some amines that are positively charged. So water likes these kinds of groups. So if you see these kinds of groups in an organic chemical, that means there's a higher chance that the chemical is soluble in water. Okay, so basically water is breaking the attraction between one glucose molecule and another glucose molecule and dissolving the glucose. So the solid glucose disappears when you mix it with water. But then when you have a chemical such as cholesterol, and you can see it's just nothing but carbons, hydrogens. Okay, one little hydroxyl group here, which can attract a few water molecules. So clearly cholesterol is very poorly soluble in water. It's not that it's not soluble. Everything is slightly soluble to some extent. That's called the solubility. But for practical purposes, cholesterol will not dissolve in water very well. Okay, so that means we will never see cholesterol, for example, in the urine. Okay, because urine is water-based. Okay, so we don't get rid of excess cholesterol or anything that doesn't dissolve in water in the urine. Okay, we get rid of those things by other means, such as bile. Okay, so in general, organic chemicals, if they have electronegative atoms, groups such as amines and hydroxyls and so on, those chemicals can hydrogen bond with water. The water can surround those chemicals, and they tend to be more soluble than the ones like cholesterol that do not have these groups. Why is solubility so important? Well, there are many reasons. Solubility of a chemical will dictate what's the location of the chemical. Is it found in the membrane part or the oil phase of the chemical, or is it found in the water part of the cell or body? Okay, so for example, in the bloodstream, if a chemical is water soluble like glucose, it will be found in the water part. If it's not, then it has to be found either attached to a protein, or it is maybe inside a lipoprotein. Okay, so the location of a chemical depends on the water solubility. ADME, as I mentioned, this is the life story of a chemical. Very important skill for healthcare professionals to understand everything about the medically relevant chemical, including therapeutic drugs. Okay, so how a chemical is absorbed into the body, how is it distributed throughout the body, how it is metabolized, how it is excreted, the whole physiology of the chemical is dependent on the solubility of the chemical. Okay, so for example, fatty acids that are not soluble go through different ADMEs compared to fatty acids that are more water soluble. Okay, so very important. How we get rid of excess chemicals from the body. Okay, that depends, again, the excretion part. Okay, so we need to get rid of excess chemicals, and the kidneys are play a very important role, but then these chemicals have to be made more water soluble, and that's one of the functions of kidneys, of the liver. So we try to get rid of as much excess chemicals as possible to the kidneys, because the kidneys are very, very efficient way of getting rid of excess chemicals from the body. Very efficient. And those chemicals are not water soluble. The kidney modifies those chemicals, tries to modify it as much as possible to make it more water soluble so that they can be excreted by the kidneys. And we'll look at some examples such as bilirubin, and then of course a lot of drugs, a lot of therapeutic drugs. So most drugs work by affecting enzymes or signal transduction proteins such as receptors. These enzymes and receptors are mostly water soluble. So in the human body, most enzymes as well as part of the receptor that binds the signal are water soluble and are surrounded by water. So clearly water soluble drugs are better able to bind the enzyme or receptor if the drug is more water solubility, is more water soluble. So for a clinician, good water solubility of a drug is highly desirable, since it makes the metabolic, physiological, and toxicity profile of the drug easier to predict and to control. Okay, unfortunately, many drugs synthesized by the pharmaceutical companies tend to have poor water solubility and therefore poor therapeutic efficacy. So these companies spend a lot of money and time in trying to make the drug more water soluble. Crystal stone formation, another important medical application of solubility. Let's use, say, two examples. The disease gout. Uric acid. Uric acid is one of the chemicals produced from metabolism, from the breakdown of excess nucleotides. Uric acid is formed in cells and transported into the bloodstream and eventually excreted into the urine. However, uric acid has a very poor water solubility, and once the plasma levels of uric acid increases to its upper normal range, then the uric acid exceeds its solubility limit. And when this happens, the uric acid basically precipitates out of the blood. So it basically becomes a solid and gets out of the blood. So the solubility of uric acid in the synovial fluid, for example, the solubility in the synovial fluid is even lower than the solubility in the bloodstream. Okay, so that's why uric acid tends to precipitate more in joints. And then if there is a decrease in temperature, as you know, decreasing temperature will decrease the solubility. So for example, the core of our body is 37 Celsius, but way down at the toes, it will be much lower. So therefore, uric acid tends to precipitate more, for example, in the toes of the human body. And unfortunately, once this uric acid precipitates, the immune cells such as macrophages, neutrophils, and monocytes, they start eating up these precipitates and in an attempt to get rid of these things from the body. And then this process unfortunately activates inflammation, and that inflammation then eventually destroys the local tissue, and we end up with severe joint pain and so on. Okay, so gout is a disease that probably affects maybe 3 out of 1,000 people. So besides gout, there's always stones to worry about. That's so much dependent on solubility. Okay, so in developed countries, maybe about 15% of the adult population is afflicted with gallstones, okay, or cholelithiasis. Majority of gallstones are cholesterol base. As we know, cholesterol is a very poor water solubility. So most stones are cholesterol based, most gallstones. Less than maybe 10% stones from the gallbladder are pigment stones, which are made from calcium salts of bilirubin. So the liver excretes excess cholesterol as bile. Bile travels from the liver through the bile duct. Okay, so the liver is responsible for this. And from the bile duct, as you know, the bile goes to the gallbladder where it is stored and concentrated to removal of water. So bile salts and certain lipids such as lecithin help solubilize the cholesterol in bile. However, when the cholesterol concentration overwhelms the solubilizing ability of bile, it forms a sort of a supersaturated solution, and the cholesterol just precipitates out of the solution in the gallbladder as crystals, which then can, under the right conditions, lead to the formation of gallbladder stones. So most patients with gallstones may not have any symptoms, while others may suffer from excruciating pain in the upper right part of the stomach. Okay, so two examples of stone formation that depends so much on solubility of chemicals in water. So that's why it's important for healthcare professionals, if you look at the structure of a chemical, the chemical structure, you should be able to sort of get an idea how water soluble it is. Is it going to be water soluble, poorly water soluble? And that will give you a lot of information on the behavior of the chemical in the human body. Very, very important concept for healthcare professionals. Okay, so just to summarize, solubility plays a very important role in dictating where a certain chemical is found in the body. Solubility basically also dictates the ADME of the chemical, including a very important area, that's therapeutic drugs. How we get rid of excess chemicals is also dependent on solubility. As you know, the kidneys is the best way to remove chemicals from the body, and I misspoke a few times that the kidneys modify the chemical. What I meant to say was chemicals that are water soluble are easily excreted by the kidneys, but chemicals that are not very water soluble, what the liver does is it takes that chemical and it tries to chemically modify the chemical. For example, add groups such as OH or carboxyls, more electronegative atoms such as oxygen or nitrogens. Okay, and that tends to make that organic chemical slightly more water soluble, so that that chemical, or at least some of that chemical, can be excreted by the kidneys. And a good example of that is bilirubin. Okay, so, and then of course solubility is an important factor in the formation of stones, as crystals or stones. Okay, so very important general chemistry concept, solubility. So we will stop here in this video to avoid making a long video. In the next video, we will talk about other important chemistry concepts such as concentration, osmosis, and other related concepts.